From directional field emergence to disturbance localization, a Phocoustic demonstration. Two experiments are presented. In the first, the disturbance occupies most of the field of view, allowing the resulting directional disturbance field to emerge clearly. In the second, the same disturbance occupies only a small portion of a much larger inspection domain, demonstrating how the measurement process can localize subtle physical state deviation within a complex scene. It is nearly impossible to detect in a much larger relative field of view. In this demonstration, a thin film residue disturbance was intentionally created using a solution of isopropyl alcohol and dissolved salt. The disturbance occupies most of the inspection field. The resulting drift representation reveals a structured region of physical variation relative to the reference state. PASDE, physics-anchored semantic drift engine, then transforms this variation into a directional disturbance field. The arrows shown here are not manually created annotations. They represent directional gradients derived from measured physical change. Notice that the disturbance produces a coherent directional structure. Certain regions exhibit stronger directional activity than others, indicating non-uniform physical variation across the residue field. The system then evaluates the disturbance using drift-based analysis and identifies regions exhibiting elevated instability. In this tightly focused experiment, the directional field becomes the dominant measurement artifact. The result demonstrates that a subtle thin-film disturbance can generate a measurable directional structure. But an important question remains. What happens when the disturbance no longer dominates the inspection scene? Part 2. Disturbance localization in a larger inspection domain. In the second experiment, the same residue disturbance is evaluated within a much larger field of view. The disturbance now occupies only a small percentage of the inspection area. This condition more closely resembles practical inspection environments where subtle disturbances may represent only a small fraction of the overall scene. Look carefully and you can see the ring toggle in and out of view. It is nearly impossible to detect in a much larger relative field of view. However, the objective of the measurement process is not simply to generate directional arrows. The objective is to identify and localize measurable state deviation. The system analyzes the measured disturbance field and identifies localized regions of physical state change relative to the reference condition. Notice that the highlighted regions correspond directly to the residue disturbance despite its small size relative to the overall scene. Although the disturbance occupies only a small portion of the field of view and remains difficult to observe visually, the measurement process continues to localize the affected region. This result suggests that subtle surface state disturbances may remain measurable and localizable even when they represent only a small fraction of a larger inspection environment. Conclusions. Together, these experiments demonstrate two different aspects of the measurement process. The first experiment demonstrates directional field emergence. The second demonstrates disturbance localization within a larger inspection domain. Perhaps most importantly, these results highlight a recurring lesson from the Phocoustic research program. The challenge is not always developing an algorithm capable of finding a disturbance. The challenge is often developing a measurement geometry capable of making the disturbance measurable in the first place. For Phocoustic, the question is not simply, is there a defect? The question is, how has the physical state changed, and can that change be measured, localized, and quantified relative to a known reference condition? That distinction may ultimately prove more important than the disturbance itself.